Yeah, so thank you for the organizers inviting me. So, interesting talks, interesting discussions. Okay, so yeah, let me get started. So this is work. So the talk is based on work that I did with Kristen. And so, here's the archive number. Okay, and so with steady progress, in quantum hardware error correction and fault tolerance, so I think that it's more than ever, important to look for new algorithms for large-scale fault-tolerant quantum computers. So, I mean, this is, something that I'm very much, interested in. And so, this work, is, we wanted, to see if we can use ideas from, quantum channels, to prepare some interesting quantum states that could be used for algorithmic purposes. Okay, and I thought that I divide my talk, that I explain the details to you at different levels of scale, starting from a general overview and then going more into the details. But if you have any questions during the talk, please don't hesitate to interrupt me. I think I have a reasonable amount of slides, so I should be okay on time. Okay, so let me talk about sampling from probability distribution. So, many problems in computer science, physics, and machine learning can be solved by sampling from interesting probability distributions. And so Markov chains are an important algorithmic tool for generating such samples. And so, for example, one application could be let's say, you want to solve a traveling salesman problem. So maybe, you could use a, simulated annealing. And so this employs a Markov chain that is parameterized by, temperature. And, as the inverse temperature, becomes larger and larger, hopefully, you found, like a low energy solution which corresponds to a, short route. And, roughly speaking, maybe well-designed Markov chains enable us to cleverly explore exponentially large spaces, so maybe, you don't waste time looking, at solutions that are bad, so hopefully, you can focus on the ones that are close to optimal. Okay, and so let me here talk about Qsamples. So here we have a finite state space omega, and we have a probability distribution over this state space. And so I call this probability distribution here pi. And then the Qsample, so it's a state vector, and the label for the ket vector is, square root of pi. And the reason, why I write here square root of pi is because, what we do is we just, turn the probabilities into amplitudes by taking here the square root. And then, you get a perfectly fine quantum state. And so quantum algorithms leverage Qsamples to achieve speedups. So, let me give you, some simple examples. So, for example, if you have, here a finite group G, and then, you create a uniform superposition over all group elements of this finite group. So, this is the first step in quantum algorithms for solving something called the hidden subgroup problem. And the hidden subgroup problem, so it's like a general framework for thinking about quantum algorithms. And so, for example, Shor's algorithm for solving the discrete logarithm problem can be cast as a hidden subgroup problem. Okay, and what are other examples, of Qsamples? So, for example, if we have decoded quantum interferometry, so here, so the Qsample is maybe a little bit more complicated than from what I showed you on the previous slide. So here, we have a density matrix, and this Qsample is a purification of this density matrix. And so the idea, in a decoded quantum interferometry is that, you have some Hamiltonian, and you would like to prepare some high energy state, because like every optimization problem, you can switch between minimization, optimization. And so this is here a polynomial, and if the polynomial has a sufficiently large degree, then this density matrix will favor high energy states. And so, here, this is a maximally entangled state, unnormalized, and this is, something that I think, a lot of people call the quantum double. Okay, and, maybe like some other, algorithmic examples of Qsamples. So this quantum sample is a crucial ingredient for something called the quantum Chebyshev method. And this quantum Chebyshev method, it allows you to reduce the cost from 1 over epsilon squared to 1 over epsilon when estimating the mean of a random variable with relative error epsilon. And then, there are some other applications of quantum samples, for example, obtaining speedups in other applications such as finding marked elements, testing properties of distributions. Okay, so yeah, maybe this concludes, like a very short overview, like why Qsamples are interesting. Okay, so now we know that Qsamples are, useful. But now let me talk about the hardness of preparing Qsamples. So preparing Qsamples of general probability distributions is very hard. So there is, a complexity class called statistical zero knowledge. And if we could prepare Qsamples, maybe let me just start over. So, so there's this statistical zero knowledge, and there is a, canonical problem that captures the essence of statistical zero knowledge. So, you're given some, circuits, and the two circuits generate probability distributions. And then the task is to decide, are these two probability distributions close to each other or far from each other in total variation distance? But, if we could create the quantum sample, so you can maybe, imagine that, if the total variation distance between the probability distributions is small, so what this means is that the corresponding Qsamples are going to have large overlap. So, if you could create these Qsamples, you could do, I don't know, like the swap test, and then, you could decide if these two probability distributions are close to each other or not. Okay, but the mechanism that is used for generating these samples, is like more general than Markov chains. But even, if we restrict our attention to trying to prepare Qsamples of stationary distributions for general Markov chains, so this is, difficult. And so there is, this, famous problem, graph isomorphism problem. And so, for example, if you give me a graph, I can easily, choose a random permutation uniformly at random, and I can apply this permutation to the graph. So I can easily sample from all the isomorphic, graphs. But for example, like if I could prepare the corresponding, Qsample, then, I would have something like a canonical quantum witness for the isomorphism class. So this has been known for a long time that, these Qsamples could be helpful, with the graph isomorphism problem. But, it's like nobody has succeeded in, efficiently preparing such, Qsamples. Okay, so I think, the audience here is very, familiar with a lot of, the Markov chain terminology. So I can just go over it, I think, rather quickly. So here we have a transition matrix of an ergodic Markov chain on state space omega with stationary distribution pi. And so what this means is that for any initial distribution q, if we apply the stochastic matrix over and over again, in the limit, we're gonna approach the stationary distribution pi. And so, and like the total variation distance measures how close we are to the desired stationary distribution pi as the number of steps m increases. And so here you have this maximization because you're trying to choose the worst possible initial state x, And this is the probability distribution that you get after applying the Markov chain, m times. Okay, and then there is this mixing time, epsilon. So what is the smallest m such that the total variation distance drops below epsilon, and it satisfies this nice bound that it suffices like to pick like some arbitrary constant. So like let's say 1/4, and once the total variation distance drops below 1/4, you can boost it. You can decrease it to epsilon by only paying an additional price that is 1 over a log of epsilon. Okay, and so to summarize, what we did, at this very, very, very high level is that, given a certain Markov chain, so what certain means, we're gonna see that, later. So given a certain Markov chain P with stationary distribution pi, we can construct an efficiently implementable quantum channel T such that when you start in any initial state, and then you apply this quantum channel m times, as m goes to infinity, it's going to have a fixed point, which is a pure state that is a Qsample of a stationary distribution pi of the Markov chain that we're considering. Okay, and what we do is so we bound convergence. So that is how fast the trace norm distance decays as m increases using certain parameters of the Markov chain. And so what certain means, I will tell you later. And the trace norm is defined like this, for Hermitian matrices, and it's okay to just look at Hermitian matrices because we're comparing here quantum states. Okay, so let's dive into more details. So let me talk about Markov chain coupling. So Markov chain coupling is one of the most important techniques for proving fast mixing. And so here fast mixing means that this mixing time scales polylogarithmically in the dimension of a state space. And so these Markov chain couplings are at the heart of our novel quantization method. Okay, and so let me try to explain the intuition behind couplings. So like in cryptography, you always have Eve, Alice and Bob. So drunk Eve moves in Manhattan. So here Manhattan. So you have this rectangular grid of streets, and so drunk Eve moves randomly around Manhattan, and at each time Eve measures 2+ states in the computational basis, and the 2 bits determine whether Eve moves up, down, left, or right, but she cannot leave the grid. And so Eve stays where she is if no move is possible. So for example, if she's here and then the outcome tells her, move right, she can't escape Manhattan. So she's just gonna, stay here. Okay, so this is, like this very simple Markov chain that we are considering. Okay, but now what you have is, you have Alice and Bob in Manhattan, represented by the blue and the red dot. And so now the difference is that Alice and Bob, their decisions are correlated in a very strong way. So they have these Bell states, and they measure the 2 halves of the Bell states, and then obviously if everything's fault tolerant, then whatever Alice will measure, so the same measurement Bob is also gonna get. So what this means is that if Alice has to go to the right, then Bob will also go to the right. And so the rules for moving are the same as in the previous example, as in the Eve example. And I mean, it's not difficult to see that viewed individually, they move just like Eve. So if you only look at how Alice moves and how Bob moves, so they will just around like Eve. But it's also not too difficult to see that eventually Alice and Bob will find each other. And do you have an idea why this is the case? That they will eventually find each other?
Yeah. Alice hits the wall, Bob keeps going. They get closer.
Yes, exactly. So for example, you can see that the distance between them can never increase. So if Alice moves to the right, and then the outcome says, hey, Alice, move again. She can't. But in the meantime, Bob is gonna get closer. So if you go to Manhattan, just bring enough APR pairs with you. Okay, but okay. So this was like the intuition. What it means. What a coupling is. Okay, but now what is the formal definition of Markov chains? And maybe like before I dive into the details, just a warning. So here we have omega times omega. So please don't confuse this with a two-dimensional grid that we had on the previous slide, because omega, so this is the state space, and the state space of the Markov chain in the previous slide is the grid. Okay, so X is the position of Alice, and Y is the position of Bob. Okay, and so this formal definition of a coupling is that each component viewed separately undergoes transitions according to the original transition matrix P. And so this is expressed by these two formulas. So Alice is somewhere, Bob is somewhere, and then you make one move, but then you don't care where Bob ends up, so you only care where Alice ends up being, and so this probability distribution is the transition probability distribution of your Markov chain P. Okay, and the other important thing is that the two components remain together forever once they have met. So what this means is that if Alice and Bob are at the same spot, and then they both make like some random move, they're gonna be together at the in the next time step. So they cannot go to different locations, and then we also want to have this symmetry condition. Okay, and so what is the connection between coalescence and mixing time? So let here xm and ym denote the random state of the coupling of this big Markov chain that starts in this initial state x comma y, and after we make m transitions according to the transition matrix C, and C is the transition matrix of the coupling. And so let tau here coalescence denote this random variable. So what is the smallest time m such that what is the smallest m such that Alice and Bob are at the same spot for the first time? And so this is called the coalescence time for the initial state x comma y. But to keep the notation, like not to overload it too much, I'm not gonna put here, like some kind of x comma y, just to keep it simple. But like this coalescence time, definitely depends on the initial state, because if they already start at the same spot, then the coalescence time would be, I guess, 0 or maybe 1. But like if they start at opposite ends of Manhattan, it's gonna take them a while to come together. Okay, but like why care about this this coupling, like if you have one problem and you want to bound the mixing time, and you invent some other problem, so then this new problem better help you solve the original problem. And so what one can show is that this total variation distance can be upper bounded by the probability that the coalescence time is larger than m. Okay, but like the details are not that important. There's this nice book you can read about couplings and Markov chains in general. But what's important is that the problem of showing that the Markov chain with transition matrix P mixes fast, so this reduces to the problem of constructing a suitable coupling with transition matrix C, such that and you want and then you have to show that this coupling coalesces quickly when starting in any initial state. Okay, and so the important thing is that the coupling has to satisfy some constraints, and it's not just an arbitrary transition matrix, but you still have like a lot of freedom how you design it. And so like the art is designing a suitable coupling and showing that it brings Alice and Bob quickly together. And if you manage to show this, then this implies by these bounds that the Markov chain mixes fast. Okay, and so what Kristen and I, so what we did is, so in analogy to the mixing time, it is convenient for our analysis to introduce something called the coupling time. And so like, I mean, this is very, very, much related to this random variable that I, called, tau. But like, let's not worry about this. Like, so this T couple is the smallest m, such that the probability that they have not come together is less than one quarter. And do you remember, like when we talked about this mixing time, we wanted, like this total variation distance be smaller than one quarter. So like this constant here, I mean, you just have to choose something. Okay, but do you roughly, so do you understand what this T couple means? Okay. 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 So let me try to get across the intuition how you turn a coupling into a quantum channel. And so, using quantum notation, we can express the transition matrix like this. And I mean, you should hopefully, all understand this, So, this here you have, these bras, and then so, the state x comma y is going to transition to this state, with this transition probability. So, we just have, written the transition matrix using the bracket, the cat bra notation, bracket notation. And so and so the classical map C acts on cat vectors of this form and maps them to convex combination of cat vectors. But in contrast, a quantum map, so a quantum channel E, must act on order products, that look like this. So here we have an order product, cat X, bra Y, and map them to linear combinations of order products. And so the question is, how can we cook up a useful quantum map T based on this transition matrix C? But maybe you can kind of like appreciate it that because here we have order products, so we have two components, and a transition matrix of a coupling has two components. So at least like there's hope that maybe you can use a coupling to construct a quantum channel. And so like this is like initially how we started, and then we were trying to see like what we have to do to make it work. Okay, but so let's C be the transition matrix of an arbitrary coupling of an ergodic Markov chain with transition matrix P and stationary distribution pi. And so this is our definition of a quantum channel. Okay, and I use here star to denote the dual of the quantum channel. And hopefully, later, you're going to see why it's more natural to define the quantum map in the dual picture. Okay, and I think, stuff like this, I think, you've seen probably, many times. So D is a diagonal matrix, and along the diagonal we just write down the entries of the stationary distribution. And so you have a super operator T star, and then before you apply this super operator, you hit whatever with square root of D from the left and right. And then once this map C star has acted, upon this here, then you hit it from the left and right with the inverse square root, and so this is a similarity transformation. Okay, because like we assume that the Markov chain is ergodic, so everything is all the entries are non-zero. And so the quantized coupling T is defined as the dual of a linear map T star with respect to the Hilbert-Schmidt inner product. Okay, and maybe like one thing that I wanted to mention is that, for example, like when you have the Gibbs distribution, you always have this issue with the partition function. The partition function is, really hard, to compute. But the nice thing is that because, here we have inverse, then, the two partitions functions, cancel each other out.
Sorry, one question. Is it obvious that C star is completely positive?
No, so it's not obvious. Okay, so so later, I will have a slide. Where I show that. So there's something called, a grand couplings, and for those, it is completely positive. But you can also have, a different, coupling where it goes wrong. So you cannot do it for any couplings. Okay, and yes, so I think you must see the future. Okay, so this here the slide, like so like let's see be any coupling. So the quantized coupling, you can always show that no matter what coupling you have, that it's always trace preserving, and you can also show that this here is a fixed point. But what can go wrong is the complete positivity. Okay. Okay, so yes, so this is what you were asking. Assume that C satisfies certain additional conditions so that the corresponding T is also completely positive. And then what we can show is that given any rho, the quantized coupling converges to this Qsample in trace norm distance like this. And what we have to do is we have to choose M to be greater than this here. And so you can see, that, like in some sense, the mixing time of the quantum channel is governed by, T-couple. And, this, I know we think that this can be improved, but, like this is what we are able to show. But, so like one of the open problems that I have, if I ever get to the final slide, is, if it's, possible to, improve this, a little bit.
By how much? How much do you think you can improve to?
Say again?
How much do you think you can improve that to?
I don't know, but like when I think like we did some, I think, I don't remember like some examples where this didn't, show up for some special case. And I think, later, you're gonna see why we get this, T star. But, but the nice thing is that, the logarithm, like, decreases it significantly.
Yeah, so how you compare this quantum result with the classical parts? Are they basically the same?
With what?
So how you compare this quantum result with the classical parts? So I do think when you have the coupling matrix and also T-couple on the classical board, you can also derive some mixing time.
Like I'm not sure if I understand your question, but maybe, like sampling, from the probability distribution, is significantly, simpler than preparing a Q sample. And I think, like I tried, like arguing that, you cannot hope, to do it for general random processes to prepare these Q samples. But, if we take, maybe there's like one thing that I should have, emphasized, so the coupling, this transition matrix of the coupling, so this exists, in your head or, on a piece of paper when you write down a mathematical proof that your Markov chain mixes fast. So you don't, run it on a classical computer. But like we take, the coupling and turn it into a quantum channel. And so I think, I mean, at least, I think, it's interesting that, like you can, relate, the quantum mixing time to the coupling time of the classical Markov chain.
Okay, so basically what you do here is on the quantum computer, you are doing some task which is much harder, but
Which is
much more difficult.
Yes.
But the computation cost or time are like
Similar, like yes, up to this here. Yes. And like for independent and grand couplings, the resulting quantized coupling is completely positive. So this was, your question. And the quantized coupling can be implemented efficiently for something called sparse grand couplings. But I think, pretty much, like all examples, that people come up, I think, most of them are sparse grand couplings. Okay, how much time do I have? 15 minutes? Okay, so maybe I need to speed up a little bit. Okay. But so the Qsample is a fixed point of the quantized coupling. So we have this here. And let me just, show how you go about proving this. So, recall that this matrix D is defined like this. So it's this diagonal matrix, and along the diagonal, we just write the stationary distribution. And what you can do is, you can write the Qsample, so this is the very definition, but you can just apply the square root of D to the all ones vector here. So this is how you can rewrite the Qsample. And now what you can do is, so this is this map C, and like if you think back a couple of slides, I defined C star, the dual, but like so. If I have C, so this is the definition here. So basically, like these things, had to be flipped, But, when you plug in this all ones matrix here, then obviously, this is going to be here, overlap 1, here overlap 1. So this y prime and x prime, so this expression just disappears. And, if you are somewhere, you must go, somewhere. Because, this is a stochastic matrix, so, you cannot lose probability mass. So this is why you just get, 1 when you sum over x prime and y prime. So you get this thing, and this thing is equal to this. So what you see is that, this all one matrix is a fixed point of this map C. And, the similarity transformation is, to make it work, for the Qsample. So like now, if you insert the projector onto the Qsample, so I think, you can kind of see that this, inverse square root of D, it will change the Qsample to the all ones vector. Then we already established that this all ones matrix is a fixed point of C. And then, we get this here, and then we need to transform it back to the, Qsample. Okay, and hopefully, I can explain a little bit, of the idea, like how we prove, convergence, So, like, let's say if the task is to prepare the Qsample, it could be any pure state. So how can you check, if you did a good job of, preparing, this desired state? So what you do is, you have, a binary POVM. So this is the projector onto the desired state, and this is, the complementary projector. And so what you want is, so basically this is the probability that you detect a bad, outcome, and, like the probability of, of the probability of not preparing, the desired state, the Qsample should be small if you run this quantum channel for sufficiently many times. So like imagine, like assume we can find an integer m for some epsilon that this here is true, then we can show that this here holds. And so this, the proof of this technical result relies on some fundamental tools in quantum information processing, such as the gentle measurement lemma and the data processing inequality. Okay, so the idea is that, like we have to show that this trace is small. But now what we can do is, we can switch from the Schrödinger to the Heisenberg picture. Okay, and so I've attempted to do this here. So, this is a probability that we detect a bad outcome after m steps of the quantum channel. Now we move to the Heisenberg picture. Okay, then we can just, say here less or equal because, this is a quantum state. Now we have, the definition of our quantized, coupling. Okay, and now you see the bad guy. So this, so like why do we have, this T star is that when we have, this trace expression, so we have, on the left and on the right, the inverse square root of D. So this is, how this T star comes about. So this is, this is what we, what we get. Okay, and so let me continue a sketch of the convergence proof. So, here I have to, sweep, like some details, under the rug. But, just to give you a, the intuition is what Kristen and I, so what we showed is that this rescaled projector can be written as a convex combination of quasi-particles. And these quasi-particles correspond to elementary graph Laplacians. So, here we have, this state ket x minus y, and, the other product corresponding, to this state. So this is this elementary graph Laplacian. Okay, and so now what is important is that this map C star scatters these elementary graph Laplacians into substochastic combinations according to this formula. Okay, but please, notice that if x equals to y, then this thing is just, the null vector. Okay, and so, what you can show is that, the power C star to the power m annihilates this quasi-particle whenever the coupling, the transition matrix of the coupling coalesces x and y. So whenever, x and y, become equal, what this means is that, this elementary graph Laplacian, just disappears. Okay, so this, C star, acts on these elementary graph Laplacians as a substochastic matrix. Okay, so this was, yes?
So you mentioned that you need to assume it's completely positive. So in this proof, does it?
No. So no. So I said that I had to sweep a lot of details under the rug, but the idea is, I think, that every quantum map you can write it with the help of Krauss operators. Okay, and then the Krauss operator hits the ket vector, and its dagger twin hits the bra. Okay, and somehow, so whatever the Krauss operator does, its dagger twin does the same thing, And so there are couplings, where what the left side does is a little bit different from the right, and this would result, in something that cannot be expressed, using, Krauss operators. And so in our paper, what we did is we found, some coupling that's not totally crazy. It appears in this Markov chain book, and then, when you run just some very simple numerical experiment, you see that the resulting, quantum, I should not call it quantum channel, but, the super operator is not completely, positive,
Yeah, but it could be still converging. It's just not physical.
It could be what?
I mean, it could be that your theorem of convergence still holds.
Yes,
That's not a physical channel.
but then you would need something different from a quantum computer that you can implement it. No, but I agree that mathematically you could prove it, but okay, yeah, but okay, so okay, so 6 minutes, but okay, so let me just go through this really quickly. So what is a grand coupling? So a random mapping representation of a transition matrix is a function that acts on the state space, and here this calligraphic R is just some domain, and you have a random variable such that this equality here holds. Okay, but this looks like something, I mean, this looks, unnecessarily, complicated. But basically, if you think about the Alice and Bob, example, so here, omega. So this is the grid in Manhattan, and then this R would be the 4 different bit combinations. You just go up, down, and so on, and then the successor state is either increase or decrease the x or y coordinate, and just stay where you are, if you were to leave Manhattan. And so the transition matrix can be written like this, okay, and then the transition matrix of this grand coupling can be expressed like this, so this decision, if Alice should move to the left or right, Bob has to do the same thing. So this is, so you see that, this randomness, is reused. Okay, and this is like not that like maybe like that important. So for example, you have these grand couplings. So you have like random colorings. So you have a graph, and you would like to sample uniformly at random from all the admissible colorings. And admissible means that no two vertices that are connected receive the same color. And then what you can do is you can set up a metropolis chain for this. So you just select a vertex D uniformly at random and then select a new color. And if this new color is allowable at V, then the vertex is assigned this color K, and otherwise no transition is made. Okay, and so basically this shared this randomness is choosing a random vertex and also choosing a new color. And so for example, if you selected this one, you can recolor it, so that's okay. And what you can show is, this is not something that we have shown, so I'm just giving you an example, from the book on Markov chains. So a grand coupling, generates this vertex to be recolored and this, new attempted color uniformly at random and applies the corresponding recoloring update to both, components. And what you can show is that, if you have enough colors, so you have enough wiggle room, this coalescence time, the probability that it's greater than m, it goes down, exponentially. Okay, and so what we can do is, so the implementation is, so we assume that we have a random mapping representation such that we can efficiently compute the images and pre-images of the function, and you can do that, for example, for the example that I just showed you, this recoloring, of the graph vertices, and assume that we can also efficiently compute the probabilities, and that we can also efficiently compute the ratios. And so remember, computing ratios, that's okay, because, the partition function goes away. And then, the Krauss operators of the quantized coupling are, are sparse. Okay, and so here I'll have to, sweep a lot of details, under the rug, but, you can just, invoke, a lot of, very cool results. So for example, if a matrix, is sparse and its norm is less or equal to 1, then there are mechanisms how you can, efficiently, block encode. And then if you can block encode the Krauss operators, there is also a quantum algorithm how you can, efficiently simulate the corresponding quantum channel. Okay. And maybe, like 50 seconds or so, but so, we can efficiently construct, okay, so maybe I just say like this, like in our paper, I just, we just wanted, to just like explain a little bit, like the intuition, how you can block encode these Krauss operators and how you can simulate the quantum channel, but like Chun-Hao Wang, I think, is here, he has a paper on how to simulate quantum channels. So, he has, like a lot of, details, like what if, these block encodings are not perfect. Okay, but maybe let me just go to the last slide, and so some open problems. So, for example, improve analysis of convergence. So, for instance, can we avoid this factor, I think, it'd be, maybe it's like not the most important thing in the universe to do, but, it'd be definitely nice to see, if you can, improve it. And then, I think, that would be kind of cool, to generalize the quantum setting. So imagine that we have a fast mixing quantum channel E. So for example, this could be a quantum channel that prepares the Gibbs state, sigma. And could you design a quantum channel, I call it, E pure, that has this purification as fixed point and converges to it quickly. But like I have no idea how to do that. I mean, I don't know if there's like something like a generalization of couplings to the quantum setting. Okay, but I think So thank you. This is my last slide. So thank you for for listening to me. I hope it was interesting.